Welcome back to another one of my learning applications of differentiation videos. We'll be focusing on maximas and minimas, or extremas, or extremas, or maximums and minimums. I'll just get rid of this light. There we go. And yeah, so we'll be finding maximas and minimums throughout this video. So let's get started with our function. Hopefully you've watched the previous video, because that'll give you the basis of what we're going to do in this video. So we grab the function. I've got the function x to the power of 4 plus x to the power of 3 plus x to the power of 2 plus 1, and it's within the domain of -1, x, and +1. Okay, now what we're going to do is we're going to find the derivative, use the derivative to help us find the critical numbers, use them to find the critical points, and once we have the critical points, use the first derivative test to find the shape of the graph and locate the maximas and minimas. Okay, so let's start with finding the derivative. Derivative of x to the power of 4 is 4x to the power of 3, plus the derivative of x to the power of 3 is 3x squared, plus the derivative of x squared is 2x, and the derivative of 1 is just 0. Okay? Now, what we're going to do is we're going to let this derivative equal 0. It'll make sense if you've watched my critical points videos, but we let it equal 0, and then we find the x value. 0 equals 4x to the power of 3 plus 3x to the power of 2 plus 2x. Now, what we're going to do is we're going to factor out an x, because if we factor out an x, we're left with 4x squared plus 3x plus 2. In this state, just this bit here, we can use a quadratic formula to solve, and this bit here, we can just solve on its own. So what we do is we split them off, and we make the 0 equal to x, and we split it off over here and make the 0 equal to 4x squared plus 3x plus 2. Now, here says it all, 0 equals x, therefore, our first critical number is 0, is when x equals, when x equals 0. And for this bit over here, we use the quadratic formula to solve. So we have 0 equals, the quadratic formula looks like 0 equals ax squared plus bx plus c, and to find x we do -b plus or minus the square root of b squared minus 4ac all over 2a. We consider 4 to be a, 3 to be b, and 2 to be c. We sub in as accordingly, so -b, that's -3, plus or minus the square root of b squared, which is just 3 squared, minus 4a, which is 4, c, which is 2, and all over 2 multiplied by a, which is 4. Now, the only problem with this is that when you simplify whatever's in this, you'll get -3 plus or minus the square root of -23 over 8. And that's a problem because that's a negative within a square root. If you put this into your calculator, this negative square root, the square root of -23, it'll spit out a math error, which is because it can't be done. Okay? You can't square root a negative number. It just doesn't work. So, that means that this x value does not exist. Okay, so there's no critical number here. So the only critical number we have to work with is at x equals 0. Therefore, our critical numbers, or number, is just x at x equals 0. Now we have our critical number. What we do is sub it in. Well, we use that to find the critical points. And to find the critical points, we sub that x value back into the original function, which would be the x to the power of 4 plus x to the power of 3 plus x to the power of 2 plus 1. And it spits out a 1. Tick. Because it spits out a number, whether it's negative, positive, or it's 0, it spits out a number. Therefore, it's within the domain of the original function. Okay? So it's a critical point. It's officially a critical point. And also, you don't really need to do this most of the time, but I'm going to put down when x equals -1 and when x equals +1, which are the domain, because it has x is greater than or equal to -1 and x is less than or equal to 1. Therefore, I'm putting down the endpoints, which are, well, you'll have the graph. It'll start at a point, which will be at x equals -1, and then it'll do some loops or whatever it wants, and then it will finish. Probably not loops, but it'll go up and down and swirl and whatnot, and it'll finish at positive x equals +1. And so I'm going to put down these these points, okay? Because most of the time they will spit out. It should spit a number. Like if we sub this into a function, we'll get 2, which is a tick. It's a critical point because it spits out a number. If we sub this in, this +1, it'll spit out 4, which is tick. And that's expected because you wouldn't have a question where the domain is not a critical point. Like you start where you start, you can't actually start unless it's like a trick question, or you just wouldn't do that because you wouldn't put it on a point where it's not defined. But I usually just do this anyway, just because I need this fx value and this x value later on when I locate my maximas and minimas. But when you're just doing the standard first derivative test, because that's what this is at first. Oh no, this isn't. Come on. When you're doing this, you're just testing to see if it's critical points, and I'm getting off topic here. Anyway, so the first derivative test. Getting ahead of myself. First derivative test is when we have our x values and we space them out. So here I'm not going to put the domains on because I know that they're endpoints, so there's no point putting them on there on this, because if you've watched the last video, we used these x values, we sub them into the derivative, and then it gives us a positive or negative gradient or no gradient, 0, and we find the shape. And I'm only gonna put 0 in here and find what's going on either side of 0. I'm not gonna put these endpoints in because I know they stop there. So if this is negative, I know it's going down from 0 to the x equals -1 direction, and I know if it's going up here, it means that it's going upwards to this direction. There's no point putting these in, it just takes up space. Anyway, so here we're going to pick a number on it in between -1 and 0, which will be -0.5. And on this side, we've got to pick a number between 0 and +1. So we'll pick 0.5. This 0, if we sub 0 back into the derivative, we'll get 0, which means it has 0 gradient. It's flat. If we sub -0.5 in, we'll get a negative number. Doesn't really matter what the number is, we just get a negative number. Therefore, the gradient is sloping downwards. If we sub the 0.5 into the derivative, we will get a positive number. Therefore, the gradient is sloping upwards. So we have a general shape now. The shape being looking something like this. It just looks like a very stretched out U, just a loop just a U, I guess. It's not like a smiley face without the eyes, I don't really know. So it's just going to go like that, which means at this point here, which is at 0, its lowest point where the tangent is flat is its minimum. Okay, and we're going to have these little circles. In the last video I did arrows, which indicated because we're in the domain of negative infinity and positive infinity, which means that it just goes on forever, so we use the arrows to say it goes on forever. Here we use the dots to signify that it stops, because it does stop. It stops at x equals that point, and x equals this number. It stops there. Okay? Anyway, so we can say that minimums, I'll grab another sheet. Where do our minimums lie? So where do our minimums at? Well, we can say that the x equals -1, it goes up to this point, so that must be a maximum of some sort, and x equals +1, it goes up to that area, which means those both of them are maximums of some sort, but this is the only minimum because it comes down and then it goes back up. Therefore, we're at the lowest point where it comes down, that's its minimum. Therefore, and that's at x equals 0, and at x equals 0, y, or the function, equals 1. Therefore, our minimum is at 0 and 1. Now, our maximums are at x equals -1 and x equals 1, because x equals -1 will be over here somewhere, and x equals +1 will be over here, which means it goes up to these points. Therefore, the maximums are at these points. Because it comes up and stops. Therefore, if it comes up and stops, we can, some people argue differently, but if it comes up and stops, because we're stopping it there, some people like to consider this as being a max, as well as this being a max, and this is the min. Okay, so we're going to say the maximum is at, first one will be -1, x equals -1, and we said that when x equals -1, the function, or you could say y, equals 2, and when x equals 1, and the function, or y, whichever one you use, will equal 4. Okay, now, judging by what we have here, we can make a new graph, and that new graph will, I'll show you what the real graph looks like in a minute, but it'll show that the minimum is at, here's the function, we have fx, and we have our x values, and it starts at y equals, or fx equals 1, so it'll start here. That'll be the minimum point, so it must be coming down from here and down from here, but it stops here. Okay, and 0, which is here, 0x, which is there, and up 1. So that's our minimum point. That's our minimum point. Maximum at -1, let's say this is -1, it goes up, let's say this is 2, and this is 4. So it goes up to 2, which means it dips down like this. And this at +1, function, or y, equals 4, so it'll be up here. Therefore, we can say that at here, this is our lowest point across the whole section we're looking at. It's a very small section because I've got a small graph, but it's out of the whole lot, this is the smallest point. Therefore, we can not only say it's the minimum, but say it's the absolute minimum. Therefore, this is an absolute minimum. Here is higher than this. This is a maximum, and so is this, considered to be a maximum. But this point is higher than this one, which means because this is the highest point on the whole graph. So therefore, we say that this is the absolute maximum, which is 1, 4, which is this one here. And this point here, it's still a maximum, but it's not the tallest maximum. Therefore, it means it's a maximum, because a maximum means they've got, like, this is the highest point. It means on either side or one side, it's got a lower value than it, which means it has the highest value than the ones around it. has a highest, the function is a higher value than these other points. The function or the y will equal anymore. So it's a maximum, but it's not the highest. It's not the absolute or the global maximum. Therefore, we call it a local maximum, which means it's high, but only to the things around it in its local area. It's high, but only in its local area. Okay, this is high over the whole thing. That's why it's absolute. That's why this is local. Okay, and the real graph, if you're interested, basically looks like what I just drew. So you have, you're gonna have 1, you're gonna have -1, and I put 5 up here, and it goes about there, and about there, and here's about 1. And it has dots or hollow dots, whatever. If it arrows, it means it goes on forever. If it's dots, it means it stops there. And this will be our fx, and this will be our x. So basically what I drew before, absolute maximum, local maximum, absolute minimum. Okay, well, I hope you learnt something from this video. Thanks for watching, and I hope you had a good day, or have a good day.